If you zoom in far enough, past the cells in your hand and the molecules that make them up, you enter a landscape that defies common sense, the atomic void. For nearly a century, studying this world required massive, million-dollar cryogenic freezers. These machines are built to solve a single, massive problem: heat. Specifically, they aim for absolute zero. This is the theoretical point where all atomic movement stops completely, a state even colder than the vacuum of deep space. To a subatomic particle, the air in a normal room is not a gentle warmth. It is a violent, chaotic influx of kinetic energy. Imagine trying to perform a delicate surgery in the middle of a wind tunnel. At room temperature, nearby atoms vibrate and collide so aggressively that they instantly shatter any fragile quantum information. However, researchers have recently found a way to maintain stable quantum connections without the deep freeze. They have successfully achieved communication at room temperature. By bypassing the requirement for extreme cooling, we are removing the primary environmental constraint that has kept quantum technology confined to specialized laboratories. This solution doesn't require a warehouse-sized refrigerator, but rather a specific design on a standard silicon chip. At the center is the qubit. We visualize its spin as a microscopic compass needle. A classical bit is either up or down, but a quantum particle hasn't settled on a single direction. Existing in all possible configurations simultaneously is called superposition. This ability to process multiple states at once is what gives quantum systems their potential power, but it also makes the qubit highly sensitive to the wind tunnel of thermal noise. To protect the qubit, scientists are using a material called silicon carbide. It is a synthetic crystalline compound made of silicon and carbon, known for its extreme durability. Inside this crystal is a rigid, repeating geometric lattice. Occasionally, these structures contain a tiny, naturally occurring empty space, a perfectly shaped pocket in the center. Researchers realized they could use these microscopic defects as miniature cages. By trapping a single electron inside, they can isolate it from the rest of the world. The rigid crystal walls surrounding the pocket function as a physical shield, or a shock absorber, against the heat of the room. The cage dampens aggressive environmental vibrations, turning the chaotic heat into a faint, manageable hum. To interact with the trapped electron, scientists use photons. Photons are elementary particles of light that carry information in precise pulses. Because the crystal is transparent, these light pulses pass directly through the protective cage to read and write the electron state, all while destructive heat is kept at bay. This proves that we can protect quantum data through clever structural engineering, rather than relying on massive cooling systems. Once we can protect a single qubit at room temperature, the next step is to link two of these shielded electron spins together. This connection is called quantum entanglement. Entanglement is a phenomenon where particles become so deeply linked that the state of one is tied to the state of the other, regardless of the distance between them. It behaves like two ballet dancers performing the exact same choreography in perfect synchronization. In this linked system, measuring one particle tells us the state of the other. If one electron is spinning up, its entangled partner is guaranteed to be spinning down. This reality was so strange that Albert Einstein famously questioned it, calling the effect spooky action at a distance. There is a misconception that these particles send messages to each other faster than light. They are not, which means Einstein's theory of relativity remains fully intact. No signal is actually being sent back and forth. Instead, the two particles behave fundamentally as a single, unified object. Today, researchers are working to scale these mechanisms, aiming to build networks of hundreds or even millions of these protected particles. By using silicon carbide cages to shield these connections from environmental noise, we have cleared one of the most significant physical hurdles in the field. This critical move away from the deep freeze marks the exact moment quantum technology finally enters the real world.